It's nice to have you today. In the last couple of lessons, we've looked at how we can try and estimate or figure out limits numerically and graphically. However, sometimes these methods don't really produce accurate results. We can think of the example of sine of pi over x, the limit as x approaches 0. And so what we want is we want some algebraic properties that will allow us to calculate limits a little bit more systematically. And so today we're going to look at several limit laws that will help us in evaluating limits. Let's start with the first few. So for these laws, we're going to suppose that c is a constant and that the following limits exist. The limit as x approaches a of f of x, and the limit as x approaches a of g of x. So we're assuming we already have a couple of limits, and if we have those, then the following are true. If we want the limit as x approaches a of the sum of those functions, f of x plus g of x, we can just add together the limits of the individual functions. So in plain English, we can say the limit of a sum is equal to the sum of the two limits. The second law is very similar, but it's looking at the differences. If we take the limit of a difference of two functions, that's equal to the difference of the individual limits. This means that if, for example, we're looking at a polynomial or something like that, something with multiple terms, and we're taking the limit, we can just take the limits of the individual terms and add and subtract them together, depending on if they're being added or subtracted. The third one says that if we have the limit of a constant times a function, we can take that constant and pull it outside of the limit and just multiply the limit of the function by that constant. Okay. The fourth one says the limit of a product is equal to the product of the individual limits. And the last one says the limit of a quotient is equal to the quotient of the limits, so long as the limit in the denominator is not equal to 0, in which case it would be likely undefined. So we have these laws that allow us to take known limits and apply them in situations where we've got sums and differences and products and quotients. And if we add in a few more rules, we can do some really interesting things here that's going to save us a lot of work in the long run. So let's look at the next one. This next one requires that n to be a positive integer, and it says if we have the limit as x approaches a of a function raised to the nth power, we can just take the limit of that function and raise the result to the nth power. And this is a direct result from taking the fourth law and applying it repeatedly. Because when we raise a function to a power, like the third power or the fourth power or the fifth power, we are just taking that function and multiplying it by itself 3 or 4 or 5 times. And if we use this property, we can pull out one of the factors each time and end up having the limit of a bunch of functions being multiplied together being the product of all of those limits. And when those functions are all the same, that ends up being the limit to the nth power. Now, to apply these limit laws, we need to know what some individual limits are, because for all of these, we need to know that these limits exist, and we need to be able to know what those limits are. So we've got 2 more laws that are going to help us out. These are 2 very basic limits. Number 7 says the limit of a constant function as x approaches a is just that constant, which should theoretically make sense. This function is independent of the value of x. The function is always equal to c, and so no matter what's happening to x, it's always going to be c, which is, we can't say closer and closer to c, it is equal to c. So in a situation like this, the limit is just the constant. And then number 8 says that the limit as x approaches a of the function x is equal to a. And that should make some intuitive sense. Here we're looking at what happens when x gets closer and closer to a, and we're asking what happens to x? Well, obviously it's getting closer and closer to a. So the limit there is a. And if we take this number 8 and we put it in as our function for number 6, then we end up having another one that says the limit as x approaches a of x to the n is going to end up being a to the n. We get that by taking this limit that we already know and plugging it in here. The limit as x approaches a of x to the n is just that limit, which is a to the nth power. Now, this is going to end up being very useful along with these rules if we want to look at limits of polynomial functions. Let's do an example together. Let's consider the limit as x approaches 5 of 2x squared minus 3x plus 4. Now, here we have rules that say that if we have the limits of sums and differences, we can split it up and take the sums and differences of the limits. So we can instead write this as the limit as x approaches 5 of 2x squared minus the limit as x approaches 5 of 3x, and then plus the limit as x approaches 5 of 4. But then we also have this rule that says if we have the limit of a constant times a function, we can pull that constant outside of the limit. So we can write this as 2 times the limit as x approaches 5 of x squared minus 3 times the limit as x approaches 5 of x, and then plus the limit as x approaches 5 of 4. And once we've done that, we can use this rule right here. If we want the limit of x to a power as x approaches a, we can just plug in a to that power. So here we can plug in 5 here for 5 squared. So this is going to be 2 times 5 squared, and then minus 3 times, well, the limit of x as x approaches 5 is just 5. So that's 3 times 5. And then plus the limit of a constant function is just that constant. So plus 4. And what we can see here is that we have effectively just taken the polynomial and plugged in 5 where x goes, and we just need to evaluate that. 5 squared is 25, 2 times 25 is 50, minus 15 plus 4. 50 minus 15 is 35, plus 4 is 39. And so we have our answer, but we can see that we can do this for any polynomial. Anytime we're taking the limit of a polynomial, we can split up the terms using the sum and difference laws, and then we can pull out the coefficients using the constant factor rule. And then we can use this rule to just evaluate each power of x at the value that the limit is approaching, and effectively just plug in, directly substitute in the value of a here, the value that x is approaching. And in fact, we can do this for any polynomial or even a rational function because of this quotient, so long as we don't have a 0 in the denominator. And this is a very useful property, which we will call the direct substitution property. And it says if f is a polynomial or rational function, and the number a is in the domain of f, then the limit as x approaches a of f of x is equal to f of a, we can simply plug in the value of a into that polynomial function or rational function and evaluate it. So let's look at this in one more quick example. Let's find the limit as x approaches 2 of 5x to the fourth plus x squared minus 3. Now, since this is the limit of a polynomial and the domain of a polynomial is all real numbers, we can use the direct substitution property here. And so to find this limit, all we have to do is substitute in 2 for x. So that's 5 times 2 to the fourth plus 2 squared minus 3. 2 to the fourth is 16. 5 times 16 is 80. And then plus 2 times 2 is 4 minus 3. And so that's going to be 81 in total. So all of these properties combined end up giving us the direct substitution property, which means that now anytime we want to find the limit of a polynomial function or a rational function, so long as there's not a 0 in the denominator, we can just substitute in the number that we're looking at for x approaching, and we're good to go. No tables of values, none of that, just plug and chug.